Yeah, you probably remember dilations. For some reason, people smarter than me decided that we needed to look at them again. So let's look at them again. Remember, a dilation is just a similarity transformation, not a congruence transformation. It's not a rigid motion, because it actually changes the size of the object. Unless, of course, the scale factor happens to equal 1. In that case, it is a congruence transformation, but that's not really a dilation because you're not doing anything. Dilation either expands or contracts the original object, as you probably remember. For instance, here we have a triangle. We expand it by 3/2, and we get this triangle. Now, if we transform this triangle with another dilation, say k equals 3/4, which of course makes it smaller because k is less than 1. If k is greater than 1, it's an expansion. If k is less than 1, it's a contraction. It's kind of intuitive, right? Makes sense. After all, you're very familiar with scale models, and the scale you use is pretty much always less than 1. Scale model of a molecule would of course be much greater than 1, or you couldn't see it. But normally scale models of airplanes and locomotives and things that are in cars, things that are big, k would be much less than 1. If k equals 1, that means you're building an airplane in your garage, I guess. What about combining transformations? We've done that before, and we can combine a dilation too. For instance, if we wanted to go straight from this triangle to this triangle, which is the result of 2 dilations, all we have to do is put them together. No, we don't add them, we multiply them. So you would take 3/2, that's your first one, 3/4, that's your next one, and your resultant dilation would be the same as performing only one dilation, one transformation, which is a dilation with a factor of k equal to 9/8. 9/8 is almost 1, and that makes sense. It's just slightly bigger than 1, and you can probably eyeball that this triangle right here is just slightly bigger than this one here, and definitely smaller than this one because of the k here is less than 1. Well, here we have another example of politician trying his hand at geometry. I wish they'd just stick to messing up society and not try to foul geometry too. They're always making mistakes. And here's another one. What's the scale factor? K? Well, that's pretty good. They just got it backwards, or reversed, or upside down. It's CP prime over CP. That's the only mistake he made. Of course, that's the difference between 4 and 1/4. So, politicians probably don't care because whether it's $4 or a quarter, they just increase taxes to make up the difference. So these kind of mistakes don't mean anything to them. But for me and you and the rest of the real world, you need to pay attention to things like this. You can't just run around reversing things and expecting some taxpayer to make it all right for you. It won't happen. So the big problem here is you just flip this. It's supposed to be CP prime over CP. And the correct answer is 1/4, not 4. Now on this one, I think the idea is to figure out what the points would be without graphing them. In other words, we don't graph the original figure, the pre-image. We're just going to figure out what the vertices of the image would be and then graph the image. I think that's what they asked us to do, so no, I suppose that's what we should do. Give ourselves a little room to work here, and we'll figure out what the vertices of our pre-image are, and then we'll graph them. What do we have here? X plus 3 and Y plus 1. So, it's do it in the same order which they specified. So f becomes minus 2 plus 3, which is 1. Minus 2 plus 1. That's minus 1. What about g? Where does that go? Minus 2 plus 3, well, that's 1 again. Minus 4 plus 1, well, that's minus 3. And what about h? Minus 4, wait a minute, minus 4 plus 3, here we go. And that's minus 1. Minus 4 plus 1, that's minus 3 again. So, here are the vertices of our first transformation, our translation. Now, a dilation centered at the origin with a scale factor of 2, that simply multiplies each one of these vectors by 2. So, this is pretty easy. We get 2 minus 2. Remember, that's how scalar multiplication works. A scalar is just any real number, as opposed to this ordered pair of numbers, which is called a vector. So if we put a 2 in front of here, we get 2 and minus 2. Here, we get 2 and minus 6. And here we get minus 2 and minus 6. Alright. I wonder. We have our transformed points here. We only were asked to draw the final image, which looks like a right triangle. In fact, I'm sure it is, because this coordinate and this coordinate, or this point and this point, have the same y coordinate, which means this is horizontal. On the other hand, this point and this point have the same x coordinate, which means it's vertical. So this is perpendicular to this one. Here's our original triangle, the pre-image. We shifted it over and up. According to this, it went over 3 and up 1, which pretty well fits. 1, 2, 3, and up 1. It makes sense. But then we doubled it. This here, this is the point 1 minus 1. It becomes 2 minus 2. That's because we're doubling we're expanding about the origin, or dilating about the origin, which could be a contraction as well. We can contract with the origin as our center point, or expand with the origin as our center point. Notice that the expansion not only enlarges the triangle, it actually moves it out away from the origin, which makes sense, because we have a vector from here to here. If we double it, well, it's going to go to here, isn't it? Same thing with this. We got one from here to here. If we double it, it's going to wind up way down here. We don't change the direction of the vector when we double it. We just change the length. So, our first image when doubled becomes this, our second image. Yeah, really pretty simple. Just do it twice, that's all. If you understand transformations, then just, when you're doing a succession of transformations, after all, I think I've mentioned before, how do you know where this came from? Suppose you couldn't see this part over here. All you know is you've got this triangle, and then you applied a dilation to it. Nothing wrong with that. Or, this particular translation, you don't really have to think about the second transformation. It's just, this thing stands just alone by itself. It doesn't matter whether there's another transformation which follows it or not. It really doesn't have any effect. So the fact that they can be treated separately shouldn't come as any big surprise to you, because as I say, whatever triangle you're transforming once, how do you know that triangle wasn't the result of 15 other transformations? You don't. Which means that previous transformations can't possibly stop you from performing successive transformations. Now this one's pretty easy, really. Just have to remember that these dilations are similarity transformations, so you can apply your rules of similarity. For instance, we're given the measure of this side here, it's 3. And over here, this side is 12. So this side is definitely 4 times this one. Well, that means every single part of this image is 4 times the size of the corresponding part in the pre-image. However, if you look at it the way I did, you'd make a mistake. It's natural to assume that this bigger one, for some reason, is the image and that this was expanded. But take a look at how it's written. Here's P, Q, R, and S, and here's P prime, Q prime, R prime, and S prime. Well, the prime is our shorthand for image. In other words, P, Q, R, S. Under the transformation gives P prime, Q prime, R prime, S prime. In other words, we're going from this larger rectangle to the smaller one. So it's tempting to say that the answer is D, 400%. But you'd be looking at it backwards, like I started to. This is the pre-image, this is the image. It got scaled down. And it's kind of like this mistake that those politicians made a couple minutes ago. Because we got to put, let's just call it image. I don't like that. How about object? So we got the image of the object and the object. Well, this is 3 over 12, right? Do it the other way. It's 12 over 3. So I almost did what those dopey politicians did and reversed it and took the original object over the size of the image, which is totally wrong. You can't do it that way. It's the image over the pre-image, and that, of course, in this case is 1/4 or 25%. Now, all of these have all but one of these have multipliers. This one here, I think we could throw this one right out, because this is just a translation. Obviously, you should recognize that pretty quick by now. They're probably trying to throw you off by putting the same number on each side. I'll get to that in a second. But this is obviously a translation. You're just shifting it. For instance, if I had this one here, I would just be shifting it 3 to the right and 3 up. That's what that would do. Definitely not a dilation. What about these? Well, these do multiply. But remember, everything has to expand or contract according to the same factor. For instance, if I use this one, this would be multiplying in the horizontal direction, but not in the vertical direction. If I were to perform this transformation, which is not any kind of a transformation that we've actually studied. We studied congruence transformations and similarity transformations. This is neither. Notice how the shape has changed quite a bit. All I did was I stretched it out in the horizontal direction, but the y direction it didn't change at all. And you get the same problem with these other two. But this one, that looks pretty good. If I perform this transformation, it gets so big I can't hardly fit it, can I? Take a look here. This is what I get. The same triangle, but 3 times as big. Expanded in every direction, X and Y. Well, there's only 2 directions in this case. And the other way to see that this is our dilation is that dilations can be written as k times xy. Remember, this is scalar multiplication on a vector. And that becomes kx, ky. Well, this can be written as 3 times xy. That's the same as that. So, this is the dilation. Okay, what they asked us to do here is to take a triangle with vertices 4, 2, 4, 6, and 7, 2, and find the vertices that represent a dilation of 2 centered at 4, 0. Well, here's the point 4, 0. Here's our original triangle, the pre-image. Naturally, under dilation, it's going to be twice as big, but remember, it moves out a little bit too. Even though we don't call this a translation, when we expand about a point that's not the actual center of the object, then we're going to end up expanding distances from that point just as much as we're expanding the actual parts of the polygon. In other words, the distance from our center point to point A, well, that's 2 units. So we're going to have to double that and maintain the same direction. So this vector from here to here becomes 4, 4. Just double the length of this one. Same thing here. This is 3 units out and 2 up. So now we got to go 6 units out and 4 up. Just double both of them. And here, this one is along the same line. So we don't go left or right at all. The difference between these two is, in terms of x coordinates, is 0. But in the y coordinate, we double that, and it's 12. So what we're doing, in a sense, is considering vectors from the center point to each vertex. Maybe I can do that. If you look at it as expanding these vectors, let's take this yellow vector here from our center point to this vertex. Well, we just double it. Continue along the same line, double it. This purple line here represents a line that's exactly the same length as the first one, extending in the same direction, which doubles the whole thing and puts this point out here. Same thing here. We've got this little yellow vector that goes from 4, 0 to 4, 2. If we double it, there should be this little purple vector right on top of it, which doubles it and pushes 4, 2 up to 4, 4. Same thing here. We've got our original vector that goes from 4, 0 to 4, 6. That's a point on our original pre-image. And then we expand it by doubling this vector, maintaining the same direction, and that'll go all the way up to the point 412, which is off the page. Sorry. So you can see what we did here. We just took the vector from 4, 0 to each vertex and then doubled it, and that's where our new point would be. Pretty easy. Well, here's one which I think they're going to take a look at how areas change in a contraction or expansion. In other words, a dilation. For instance, if the dilation factor is 2, that doesn't mean that we doubled the area. We might have, or we might not have. I think in this problem we're going to find out. 8 by 10 inch photo, well, that's 80 square inches, I think. Yeah, 80 square inches at 50%. What is the area of the image? Well, if we're talking about dilation, we'll reduce each of these. It's 8 by 10. It's going to be 4 by 5, right? So our new dimensions here are 4 by 5. That's a dilation factor of 1/2. What is the area? Well, the area would be 4 times 5, or 20 square inches. And why would that be? Well, it's because area is length times width. We apply our factor k. In this case it was 1/2, so I'll use 1/2 and then we'll do it more generally. So L was cut in half, so we got 1/2 L. And W was cut in half, so we got 1/2 W. You can do a little rearranging here and we get 1/4 LW. Well, what's 1/4 of 80? 20. If this was in more general terms of k, where k is either less than 1 or greater than 1, it doesn't matter, the area will be k times L times kW. L changes by a factor of k, W changes by a factor of k, and we get k squared times LW, or k squared times the original A. The area of the image under a dilation factor of k is k squared times the original area. How many images of this side would you need to cover the original photo? Well, looks like you need 4, isn't it? I mean, the area is 1/4, and it kind of makes sense if we break it up. I mean, watch what happens. Oh, I'm not even going to try to draw straight lines. Hang on. Let's say this is 8 by 10. It doesn't really look like it, does it? If we cut the length in half, yeah, and the width in half, we end up with this thing here, don't we? Which we call 50% because it has a scale factor of 1/2. But that's really just 1/4 of the picture, isn't it? We cut this part in half and this part in half. That's like half and then half, which is 1/4. We cut this in half, and we cut this in half, and we've got another quarter, and the same thing over here. We cut this in half, half, half. As we draw our lines, we can break it up. Each of these 50% photocopies is actually 1/4 of the original. It sounds crazy, but remember, we're cutting the linear dimensions in half. It means the area is going to be reduced by 1/4. So whatever you do to the linear dimensions, you have to square that to figure out what you're doing to the area. If you double the linear dimensions, the area becomes 4 times what it was before. If you cut the linear dimensions in half, the area becomes 1/4 of what it was before. Here's one that's pretty simple. It goes back to something we looked at earlier. You put a reduction of a page. Say this is like a 75% or 50% photocopy. Explain why there is a point that it's in the same place on both pages. For instance, if you could see through, if you used really copied on a really thin tracing paper, it's probably not possible, but if you do something like that, as you line them up, you'll find that there's one point on there which doesn't change. It's not moved inward the way everything has to move inward if you're going to reduce it. But it's not. Why? Well, that's because it's the center of the dilation. In other words, when you photocopy and produce an enlargement or a reduction of the photocopy, you're creating a dilation about the center of the object, not some point outside the object. You're not expanding about the origin or about some corner of the object. You are dilating it, contracting, or expanding about the actual center of the object. And most pages are rectangular, so we're generally talking about rectangles here. And when you enlarge or reduce a rectangular page, you're applying a dilation about the center of the page. And that point, of course, will not change. It won't move. Well, that's about it.